Hello everyone, I'm Tony from Intel. Today I will present an empirical study on predicting uncorrectable memory errors for proactive replacement on large-scale field data. This is a joint work with Xiaoming Du and Shenzhou from Intel, as well as Mao Ye and Jing Li from Tencent. Here is the outline of my talk. First, I will briefly introduce the background of DRAM reliability and errors. Next, I will describe the task, the data set, and the performance measure. After that, the traditional predictors and the new predictors using micro-level information are presented for the comparative study. The experimental results are then given, demonstrating that the column fault predictor performs the best. Finally, I will give the concluding remarks and the future work. A dual inline memory module composes of a few DRAM devices organized in ranks. Each device contains a number of banks, and each bank is a two-dimensional array indexed by rows and columns. While we expect that the content read from the devices should be the same as that written, in reality it may not. There can be multiple underlying causes, to which we refer as faults. For example, soft faults like particle strike. When DRAM wears out, non-reversible hard faults get developed. Hard faults are found to be dominating in the field. In summary, DRAM is not reliable. To mitigate DRAM failures, error-correcting codes, abbreviated as ECCs, have been developed. ECC corrects the error bits in correctable errors, abbreviated as CEs. However, when errors coincide, the error pattern may go beyond ECC's capability. The coincidence then becomes an uncorrectable error, abbreviated as UE. A UE typically leads to a system crash. As a problem at scale, it becomes one of the leading causes of failures in data centers. In some environments, the cost of a server crash can be significant. In those cases, one may consider replacing the DIMM proactively before UEs happen. This requires the use of predictive failure analysis. For example, if we see 1,000 CEs in the past 24 hours, the DIMM is predicted to experience future UEs and is to be replaced. The question then becomes, what is the right policy for proactive replacement? In our study, we addressed the problem of online UE prediction for proactive replacement. There are many DIMMs on an individual server. There is also a UE predictor with access to the CE history of those DIMMs. When a new CE comes in, the error information, such as the DIMM, the bank, the row, and the column, is collected. This triggers the predictor to perform UE prediction with the new CE and history information. If a predictive UE alert is generated, the cluster manager will get informed and migrate the workloads immediately. A repair is then requested. The administrator may choose to replace the DIMM either promptly or later in a batch. The data used in our study comes from Tencent data centers. We collect the data from more than 30,000 of contemporary Skylake and Cascade Lake servers with a period of 8 months in the last year. The servers are with DDR4 DIMMs, by 4 or by 8, 16 GB or 32 GB. Hardware and software sparing features are disabled on the server. Memory patrol scrubbing is enabled on some servers. The micro-level C address information is obtained from the Linux error detection and correction driver. there are around 1.8 million CEs observed on more than 1,000 DIMMs or servers. More than 100 UEs are found. 48 UEs happen before seeing preceding CEs on the DIMMs. In our settings, those CEs are by no means predictable. Therefore, we discard those DIMMs in our evaluation. To measure the performance, we replay the error data for a predictor to run online UE prediction. If a UE occurs without a predictive alert generated from the predictor, it becomes a false negative. If the predictor generates a predictive alert at a time, we look for future UEs. If a future UE is found, it becomes a true positive. If there are no future UEs, it becomes a false positive. Precision gives the percentage of the true alerts over all the alerts. Low precision implies a waste of good DIMMs in replacement. Recall gives the percentage of true alerts over all the UEs. A low recall implies that we suffer from more UEs. Our goal is to keep a relatively high precision with a decent recall. Now we present the predictors used in the comparative study. The traditional idea is to look at the CE rate. With a high rate of CE occurrences, it is assumed that more likely UE will occur in the future. The predictor then becomes, if we see no less than theta CEs in the past 24 hours, a predictive UE alert is generated. Note that the 24-hour period is common in tracking CEs in both the firmware and the operating system. This predictor does not utilize the micro-level CE address information. In some previous field data study, it is argued that counting the underlying faults is more indicative of DIMM health than counting the observed errors. In the second predictor, if we see CEs on no less than theta unique addresses in the past 24 hours, a predictive UE alert is generated. The third idea is based on the prediction of the so-called weak cells that are likely to experience errors in the future. In the predictor, if we see no less than theta CEs on those weak cells in the past 24 hours, a predictive UE alert is generated. Here, the weak cells are determined by a simple online learning approach proposed in an earlier paper. The fourth idea is based on faults in memory I/O. For example, if there is a circuit damage or I/O drift on a bit line, the electric charge movement on the bit line will be weakened. The column then becomes error-prone. The predictor here examines the CEs in a column in the past 24 hours. If those CEs scatter on no less than theta unique locations, and the region covering the CEs spans no less than half of the column length, a predictive UE alert is generated. Now we first show the prediction results of the predictors using representative values of those thresholds. We see that the traditional CE rate predictor does not perform well with a very low precision. Examining the fault number rather than the error number slightly improved the performance, but not much. The predictor based on weak cell prediction achieves a high precision, but the recall is too low to be useful. Among them, the column fault predictor performs the best. Comparing with the traditional predictor, it boosts the precision with a factor of 3, and at the same time improves the recall substantially. We expect that using a more rigid theta value as the threshold, we get a higher confidence in prediction. Consequently, we can achieve a higher precision with a lower recall. However, in the CE rate predictor, it is not the case. Both the precision and the recall trend down given the more rigid thresholds. Therefore, we conjecture that the predictor does not capture the nature of the prediction task. However, in the column fault predictor, we see that by varying the threshold theta, we can trade the higher precision with a lower recall. Finally, we examine the UEs correctly predicted by the column fault predictor. With different threshold values, we see that more than 3/4 of those UEs locate in the exact faulty columns identified. The remaining UEs actually locate in the adjacent columns. This indicates that the predictor captures the nature of a significant portion of UEs. To conclude, we have performed a large-scale field study on UE prediction using error logs from more than 30,000 servers over 8 months in the Tencent data center. We compare the performance of the traditional CE rate predictor with some new predictors based on micro-level CE address information. The experimental results demonstrate that, comparing with the traditional CE rate predictor, the new column fault predictor boosts the precision by a factor of 3 and at the same time improves the recall substantially. In the future, we will look into more different environments on how well the results can be generalized. This is the end of my talk. Any questions or comments are welcome. Thank you.